All right, what I'm going to attempt to do is explain thermochemistry, but from a conceptual standpoint. So that way you can understand what's going on when you see these problems, and then you're not just plugging things into equations, and you're actually thinking about, okay, what's actually happening here. All right, so we have this reaction. We have elemental nitrogen plus 3 moles of elemental hydrogen form ammonia gas. And what we have given is that it's at 25 degrees Celsius and that the enthalpy of the reaction at 25 degrees Celsius is negative 92.2 kilojoules per mole. Okay, first of all, I'm going to try to explain this all conceptually. So I'm going to rewind on this enthalpy. What the heck is enthalpy? And I'm going to get all of my explanations from these things featured here. I'm going to bring this closer to you so that there's no glare, or hopefully minimal glare. So this top graph is going to come in use later, and I'm going to explain what that means in a minute. But these are really the ones we're going to use. So those top two equations come from chemistry, and those are the ones I'm going to use to explain all of those three major things: Gibbs free energy, enthalpy, and entropy. And then I'm going to use two equations from physics 2 to try to conceptualize what these things really mean. And what they actually represent when you go and do problems. But the first thing we need to know really quick is just what these variables mean. This is enthalpy, this is heat, this is moles of the reaction, specifically reaction. This is Gibbs free energy, this is enthalpy again, this is the temperature of the reaction in Kelvin, this is the entropy of the reaction. This U is the internal potential energy of a system. So that means that if at any one given point in time inside of all of these molecules there is a certain amount of energy, and the amount of energy there would be delta U, or it would be just U, delta being a change. So that would mean if there's a change from this side to that side, that would be a delta U. So the delta U, the change in internal energy on any system, is equal to the amount of work done by that system plus the amount of heat that goes into the system. So that means if this system does a little bit of work, here, I'll explain it with this one here before I even bother. Work is equal to the pressure times change in volume, and this is negative for a reason. So W is work, this is pressure, change in volume. So just to conceptualize, because this is a chemistry class and not a physics class, I'm going to try to explain these two really quickly. Especially that bottom one, work is equal to negative pressure times volume. Let's say we have a piston inside of a tube. If we have a piston inside of a tube, and our job is to see what happens with this tube here. Let's say there's a random gas in here, G, or just some random gas. If there's a random gas in there, if this gas pushes out on the piston so that instead the piston is here instead of where it was before, then that means that there is now a change in volume of about this much. Now, it is costly for this thing to push outwards like that. It is costly energy-wise for this thing to push outwards. So that means that if you have a change in volume where it's positive, that means the amount of basically we had energy in this gas here that went towards the piston, enough so to change how much it got pushed out by that much. So that means that the energy from the system went to the size of the container that the gas was in. Now, another thing too is like if you have heat over here, you pump some heat in, which will represent with the variable Q. That's more energy added to the system because heat is literally just energy. If you take some heat out, that would be minus Q. So this would be minus Q, that would be plus Q. So this is a negative just because a positive change in volume means work done by the system, which means that's energy leaving the system. So if that's energy leaving the system, that has to be a negative, even though there's a positive change in volume. And when you have to push forcefully against this thing, what you're pushing against is the pressure of the outside's surroundings over here pushing in on it. And I'm going to represent that with P. So that means that if there were no pressure out here, it would be no work done to push that thing over to the side. That's why if you're in space, you can just shove a baseball and nothing will happen to the baseball. It'll just continue moving that direction and it costs you nothing to do that other than overcoming inertia. But basically, it's just saying that the amount of work done by the system is proportional to the pressure and the change in volume. So that means that the internal energy of the system at any given point in time is how much it's done work-wise to change the volume of its container, and then how much heat you, the user, added to the thing or took away from the thing. And our system, for chemistry's sake, is always the reaction, specifically the reaction. The chemicals involved in the reaction, not the surrounding water, and that's very important. Okay, so lengthy stuff regarding physics out of the way, we're going to now move on to what the heck is enthalpy then, because enthalpy is probably the most important thing we're going to be talking about. So change in H is the symbol we use for enthalpy, and how I'm going to derive the conceptual meaning of enthalpy is going to begin with that first equation on this list here, Q of the reaction divided by the amount of moles of the reaction. Really simply, what this is saying is that if you go through with this reaction any amount, it's going to give off or it's going to take away from the surrounding air some amount of heat. This one specifically says 92.2, and because it's a negative, that means that's how much energy is leaving the system. So that means that's how much energy is leaving the molecules and entering the surrounding air or surrounding gas or surrounding anything. And it would then be divided by the number of moles of the reaction to say that this is exactly how much energy is released by these molecules per time that you go through this per mole. So that means if you have 1 mole of nitrogen, 3 moles of hydrogen, if you then go forward all the way, that amount of energy will be released, 92.2 kilojoules. So now what I'm going to do is, just to make this a little simpler, I'm going to say that for my example purposes, that the amount of times we're going to do this is equal to 1, which means we're going to have 1 mole of the reaction, which would then turn our change in H equation to just Q of the reaction, because then it would be divided by 1. So this is just saying the amount of heat change, or the amount of enthalpy is equal to the amount of heat change of the reaction. And that's exactly what enthalpy is. Heat. That's it. It's just heat. So now what we're going to do is talk about what the heck the rest of these things mean. But I'm going to first do a little bit of derivation, a little bit of physics derivation to try to conceptualize where this even heat energy is coming from. So we know that the amount of internal energy is equal to work plus Q, or work plus heat. Well, there's heat right there. Let's just say this is Q of the reaction. Then let's subtract this over. We have U minus work. Let's sub in our work equation here. So that means U plus pressure times change in volume. So that would be then equal to delta H. So that means delta H is equal to the internal energy plus the pressure times volume. Okay, so now to explain what this could actually mean if we then took this and tried to actually say conceptually what this means, it's just saying that if we have some gas here, we have some gas G. This gas, just because it's not at absolute zero, just because it's not at absolute zero temperature, there is some internal energy inside of this thing, represented by U. So there is some internal energy there. And then what this plus P change in V means is that there's also a little bit more heat energy stored in how much it's able to push back against the atmosphere surrounding it. Because surrounding it is still some atmosphere. So the fact that this gas bubble here can maintain this consistently sized cloud is evident of it having a little bit of work energy, being able to push against that pressure from the atmosphere trying to crush it. If the amount of pressure inside of this thing was 0, then the entire atmosphere around it, because it's not 0, would crush in on it, and then you would see pretty much 0 stuff here. So that means that the amount of heat energy, the amount of enthalpy that this thing has is equal to the amount of internal energy held in the molecules and everything that makes up the gas, plus the amount of atmosphere it displaces to try to take up space. to try to prove that it's there. So now let's try to sub that back into this second chemistry equation and explain what Gibbs free energy and enthalpy mean. So I'm going to erase this and put this a little bit further up here. Change in H is equal to U plus pressure times change in V. So now we have another equation. Change in G is equal to change in H plus T change in S. Just so you know, sometimes I'm writing the little knot there, the change in H knot. Sometimes I'm not, just change in H. It doesn't matter just because the knot literally just means that whatever's happening is at 25 degrees Celsius. But these things tend to stay true no matter what. The conceptual doesn't really matter. Or the conceptual part of it makes the knot not really matter. Now, if you were actually starting to talk about things not at 25 degrees Celsius, it would matter. But for now, it doesn't matter. So now let's have this change in G is equal to change in H plus T change in S. Let's sub this back in now. So that means that we can sub in this H value here for that H there. We can say change in G then is equal to the amount of heat energy, which is represented by U plus P delta V. Oh, this is not a plus, this is a minus. Minus T change in S. Okay, so that's what Gibbs free energy is, but now let's, again, this is a conceptual lesson here, so I'm going to try to explain what this means conceptually. This is the amount of heat internal energy stored inside of this gas G at any one point in time. And then what the heck could this T change in S mean? Well, again, this gas is surrounded by, I want another color. Give me another color, yes. This gas is surrounded by an atmosphere. It's surrounded by an atmosphere at any one given point in time. This atmosphere also, just because it takes up space and just because it exists at not absolute zero, has a certain amount of energy in it, because another part of this change in U equation is 3/2 nR delta T, just to say that U is equal to, or U is proportional to temperature, so that means if you have a temperature, you have an internal energy. That's another physics equation. This surrounding air has a certain amount of stored energy in it on its own. This E here. So that means if we want to go through a reaction, turn G into something else, like maybe turn G into big G. If we wanted to go from N2 3H2 to 2NH3, if we wanted to do that, instead of us having to pump in the entire equivalent of U plus P delta V, we can actually pull just a little bit of that energy from the surrounding air around it, because that surrounding air has a little bit of energy on its own. So that means we only really need to add this amount minus the energy stored in the air around it. And that's what that T change in S means. And then how you would represent the amount of energy stored in the heat around it would be the temperature times the entropy. So entropy is just the disorder of a molecule. Entropy is dependent on temperature. So if you multiply temperature and entropy, you get a unit that is equal to heat, because basically entropy would be change in S is equal to actually most of the time it's in joules. Joules per mole times Kelvin. So basically it's joule per mole per Kelvin. That might be difficult to see, but yeah. Change in S, joule per mole per Kelvin. So that means that if you then multiply this by some temperature, probably in K, you would then eliminate the temperature and the K there. So now, so now you get a new term is equal to J over moles. So that's energy per mole, which is exactly what the rest of these are. So then all that means is Gibbs free energy can tell you exactly how much energy you as the chemist need to put into the system, if any at all, in order to go through with the reaction. If Gibbs free energy is equal to 0, that means that you have to put nothing in and the system has to take nothing out of the air around it in order to go through with the reaction. So that would be something at equilibrium, because it doesn't need to take anything, it doesn't need to have anything, and it doesn't need to give anything in order for it to go through with the reaction, and it just will. So it'll be in equilibrium from both sides. Now, if this Gibbs free energy is less than 0, it means that you don't have to put much in it. It means that this value here, u plus p change in v, is small enough to where this t change in s is bigger than this u plus p change in v. It's just saying that the amount of energy formed from this here, or formed or taken away, is smaller than the pre-existing stored energy in the system. So what'll happen is the energy will just move from here to the inside and convert it on its own, because the energy is already there to do it. So if it's already there to do it, that means it's spontaneous. So it'll automatically go from that side to that side. That's all that means. And if g is greater than 0, all that means is that the amount of energy stored is going to be, or the amount of energy to go from left to right is greater than the amount of energy already stored in the air, which means this E is not big enough to change it. So therefore you as the chemist need to put a little bit more heat in, represented by this value here, a little bit more heat in to make the thing work. That's really all it means. So that's the conceptual on what that is. So now what I'm going to try to do is explain how would you calculate H's depending on bond energy and depending on enthalpy of formation, because those things do differ. And that's why I gave this change in H reaction here, because this is going to be like our place marker or check mark. If you really want to go physics, it's called a datum, to tell us that we're doing it right, or to have a reference to go back to. So I can remove this now because I don't really care. Conservation of energy states that no matter what goes on, there's still going to be a constant amount of energy in the system as there was at one point in time or in the other, assuming you have a large enough system. Which means that if our system consists of the entire reaction, that means that the amount of energy that goes from the reactant side to the amount of energy from the product side is going to be equal both ways. It's just saying that the amount of energy you get from products is equal to reactants, or if something somewhere down the road, it loses some Q heat energy, overall in the bigger system of the surroundings, so this would be the system, this would be the surroundings, overall change in E is equal to 0. Energy stays constant throughout the system. And we can actually calculate this, because what we can do then is we can just say, well, let's measure how much energy the products have. Let's measure how much energy the reactants have. And if we do products minus reactants energy, we can say, oh, that's how much is left over. It's the amount we ended with, amount we started with, which is literally just everything we've ever done with what change means. It literally just means, oh, that's a weird color. It literally just means that your ending minus your starting equals your change. It's as simple as that. Now, which ones would you know how to do, though? Which ones would you do? Because again, like I said, bond energy versus enthalpy of formation are slightly different. So let me explain what those are, again, conceptually. Is what I'm going to start, just because it's a bit more intuitive, is enthalpy of formation. So what enthalpy of formation is just saying that that's how much energy you need to form the thing from basic elements. Or that's how much energy it releases or absorbs to be formed from basic elements. So if I gave carbon dioxide, for example, we have CO2 in gaseous form. In order to form this from basic elements, what you would do is you would go this way. You would have an O2 gaseous plus an elemental carbon, probably solid. That was a great voice crack right there. Probably solid. So then what you'll have is you'll have C plus O2 form CO2. Now, one thing that we know is that elements can't form themselves based on smaller divisible parts that would still be on the periodic table. So we say the enthalpy of formation of these things is 0. So that means change in H is 0 for carbon, change in H is 0 for oxygen. There's going to be some then change in H for carbon dioxide. And that's why we have this lovely chart here of all of our thermo values. And it says that CO2 in gaseous form has an enthalpy of formation of negative 393.5. 393.5 kilojoules per mole. So that means every single time we have 1 mole of solid carbon and 1 mole of oxygen gas, we will release 393.5 kilojoules when we go through the reaction and turn it all into carbon dioxide. So that's why enthalpy of formation is just a random, like it seems like a random number, but all it means is that when you combine carbon and oxygen, that's how much energy you get out of it. And we can actually measure that amount of energy because if we do this reaction inside of another piston, if we do this reaction here inside of a piston system, where we have here another piston, if we just have like a pile of carbon here, and then we pose in some oxygen, measure how much it was before the reaction went through, and then watch the change here, in the change in volume there, we can get the amount of kilojoules that this thing went through with. And that's what they did. They did that a bajillion times and figured out the average value was around 393.5. So, just because that's the amount that this thing releases at any one given point in time, it's a negative. So that means that carbon and oxygen, when you mix them together to form carbon dioxide, they release that much amount of energy, hence the negative. So let's try to compare that to our original problem now. We have N2, H2, and H3. These are both elemental. They will have an H of 0. Oh, hey, so our enthalpy will now be very close to the enthalpy of formation, or very closely related to the enthalpy of formation, but there's 2 of them, so something will change. We will then say the amount of change in the enthalpy of formation of the product minus the change of the enthalpy of formation of the reactants is equal to the change in enthalpy of the whole reaction. So we will go change in the products, and I have a table over here so that you don't have to wait and sit for me to do all of the things. The change in H of NH3 is negative 46 kilojoules per mole. And then there's 2 of them here, so that would be a 2. Minus the change in H of the reactants. You would do 3 times 0, 1 times 0, you get 0. Is equal to, it should equal close to 92.2. So we'll say change in H reaction, 46 times 2 is negative 92 kilojoules per mole, is equal to the change in H of the reaction. So obviously that's really close, so we've done something right. Okay. And that's how it works with enthalpies of formation. So that's just saying the amount of energy that it takes to form this compound based on elemental parts is going to be equal to the amount of energy it takes to form these subtracted off. That's all it is. Okay, now let's talk about bond energy. This is the one that tends to get a little bit more feisty and a little bit more conceptual. So I'm going to pause the video here and just make sure I explain it right before all of this extra stuff gets lost. All right, first attempt at trying to explain bond formation, because I want to get this to work well, so I'm going to probably take multiple takes at this, but if we can get first take to be good, that would be good as well. So things change when we start talking about bond energies, and it's all related to this graph, that graph at the top. And I'm going to redraw it here so that way I don't have to just keep referencing that tiny graph. So what we have here is, this is the 0 line, this is potential energy, internal potential energy, and this is internuclear distance. So really quickly, what internuclear distance is, if you break down that word inter and nuclear, that literally just means between nuclei, so the distance between nuclei. So that means if you have a bond that's going on, like if you have a hydrogen molecule here and then another molecule, a hydrogen atom here and another hydrogen atom here, the distance from that nucleus to that nucleus, the distance to go from there to there would be d, the internuclear distance. So at any one given point in time, these two hydrogen molecules have a proton in the nucleus and an electron spinning around them. And now what I'm going to do is I'm going to draw a Bohr model for this, but just know Bohr model is outdated. And then I'm going to do another one here for the second hydrogen so that I can compare these two. No particular reason that I drew them symmetrical. So these are our two atoms here. I'm going to explain what's going on in terms of forces now. So this proton is positively charged. So is that one. This electron is negatively charged. So is that one. So that means that might be really freaking small for you guys to see. Either way, you can still understand what's going on. So positive, positive, repel. Negative, negative, repel. Positive, negative, attract. Yeah, basically that's how it works. And just know that the charge for an electron and a proton are equal to one another, but directly opposite. Opposite charges attract, same charges repel. So let's draw the forces on this one. Basically what we'll see is that this positive and this negative make this atom overall want to draw towards the other one. You'll see a similar force going this way. That will be a similar and opposite. You'll see the same thing going on with the other one. And we're going to ignore the intra forces that would be directly inside of this one because they're already taken account for and the system cancels them out. That would literally just be explaining why an electron circles a proton, and that's not what we're here to do. So there's a force that goes from both ones that way, and just know that the force is appropriate to the 1 over the distance squared. So that means that every single time you increase that distance by 1 unit, the force decreases by 1 over squared units. So that means if this distance goes from 2 to 4, you will see a drop in the force of 1/4 because distance increased by times 2. So that may explain why this graph is very curvy. Okay. Then at any one given point in time, there's a repelling force between the electrons that pushes them away from one another, and between the protons, which pushes them away from one another. So overall, there is a tendency for all of these forces here, because that's in the opposite direction as that kind of, and that's in the opposite direction as that kind of. So there will be an overall cancellation that results in a net force somewhere, in some direction. But just know that it's typically a net force of either this way or that way, and on the other atom as well. Just because that's how they work. And I've enlarged these distances very far, just to show how it works. So what'll happen if these two atoms come closer together? These repelling forces will get stronger, these attracting forces will get stronger, but there's a tipping point where the repelling forces actually get too strong, and will overpower the repelling forces just by how it works and some quantum stuff. And if you go and try to figure it out and see how electrons work, that's what happens. So there is a tipping point right here where if they become too close together, it actually then takes energy on part of you, the scientist. It takes energy for you to force these things together even further. It'd be like trying to push a beach ball underwater. The further you go down, the more the water pushes back up against you. Or actually, no, the more the air wants to come back up and push it back upwards. So then it takes you force to push this thing down. So then that's why you see a massive spike in this potential energy right here. And then what happens is as you get towards the threshold energy, this potential energy approaches a minimum. So that means that that would be then the least amount of energy to hold these things together in place. So this would be where the forces are at equilibrium with one another, and they're at a good distance where they like one another just enough so that all the forces cancel out, and the net force on this is 0. So therefore, they will just be locked in place or yo-yoing back and forth like this because they can never truly reach 0 if they begin at a point that isn't perfect already. Which, for most sake, is close enough to where you can say that there's pretty much no movement. And then what happens is, as you separate them, the attraction forces will start to take over instead of the repulsion ones, which means it actually takes energy to pull them away, kind of like pulling a rubber band. The more you pull it, the more it tries to pull back on you and come back together. So, therefore, it actually takes energy more so to try and get this thing together. Now, this will then asymptote towards 0 because there's a certain distance apart where it's just so far that this force is pretty much 0. So that means the potential energy stored due to the electric force between these two is pretty much 0. So that means that at this low point, that's the least amount of energy that you need to get it there. Now, this is actually a negative number. The reason why this is a negative number is because technically you're not really doing any work to get it there. You're not doing anything. What's happening is the forces between them, just because of the charges of these things, which are essential for their even existence, are doing all the work for you. So that means that since work is force over distance, that's another thing that you get taught in physics. Since the amount of work done on a system is the force over a set distance, if that force makes them move a certain amount, then that force is doing all the work. Now, because that distance is decreasing, there's technically negative work going on, so therefore you have a release of energy from the system. So that means as these things get closer together, let's say that this here is the amount that it wants to go to. When they reach that, it means that the amount of distance traveled there and the amount of distance traveled there, you see a release of energy out that way. So because there's a release of energy out that way, that means that when bonds form, it's releasing energy. And then for those bonds to break, you as the chemist have to put in energy. You have to pump it back in to separate them enough to where you can then say that they're separated enough so that they are then perceived to be closer to another atom, with which they can then repeat the cycle for. So in order to get them to that point, though, you have to pump a little bit of energy in. And then how that would work if we started talking about this again is we have, to begin with, N2, H2, NH3. Let's draw the Lewis dot diagram so we know exactly how these bonds will work. And I'm going to give a crash course on how to draw a Lewis dot diagram right now. What we first have to do is we have to evaluate what we're dealing with. We have N2. I'm going to draw all of them over here. So if we have N2, that means that you have two ends. So they're going to be bonded together in some way, shape, or fashion. But there's going to be a bond, at least a single bond. Okay? So now we're going to take a look at our periodic table and look where nitrogen is. Oh, there it is. So there's a maximum of 8 valence electrons in every single atom on this list except hydrogen. So we're going to leave hydrogen out for now until we deal with it later on. So we're just going to pretend for now it's all 8. And it decreases as you go down over here. We're going to ignore all the transition metals, so we're only going to focus on the tall blocks. So that means that everything here has 8, 7, 6, 5. So that means a nitrogen on its own holds 5 electrons on its own. So that means we have 2 of them though. So that means there's a total of 5 times 2, so 10 total electrons. So that means we have 10 electrons for us to play with, pretty much. So we're going to have them bonded, and now our goal is using 10 electrons, we need to have both of these ends have 8, because N2 does not have a charge up there, which means that they both have to have full valence shells. So what we're going to do is we're going to draw 1, 2, 3, 4, 5, 6, 7, 8, that bond counts as 2, so 9, 10. This one's full. That one only has 4, though. This one, because it's full and has more available parts, it actually has the ability to share. And that's what a bond is. It's sharing electrons. So what is going to happen is this one here is going to come down and act as the second bond for this. And then that's going to create a double bond. Now we have another problem, is that this is now 8, but now this is only 6. This one has the capacity to share one more pair, so it's going to. Now what we have is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. We're good now. Although this might get the point off. Electrons don't like to be near one another at literally any costs. So once you draw the thing, readjust it so that the electrons are as far apart, especially the lone pairs, because the lone pairs you can think of as kind of like a set of bearings on like a skateboard wheel. They can spin around all around as they need to be spinning around, but they have to stay locked in that one spot, which means that if there's a force that pushes the bearings to a certain side, it's going to follow that certain side. So this is the completed thing for nitrogen. Notice it's a triple bond. Bonds store different energies based on their distance. So notice that internuclear distance is again here. Because it's a triple bond, they're actually going to be way closer together. So there's going to be a really big spike. I want to draw this right. Really big spike down here, curves up, and then goes back that way, the same kind of way, except it's going to be further down. Oh, hello. Further down this way. And it's going to peak at a spot that is closer on the x-axis than this one, assuming this one's a single bonded thing. So now let's talk about hydrogen. Hydrogen's probably the easiest one in the world. So hydrogen, you go H, bond H. Think about how this is going to work now. Hydrogen only has 1 to give because it's on the leftmost one, but it only needs 2 because hydrogen is the one outlier that only needs 2. Helium also only needs 2. We never deal with it because it already has 2, so it doesn't care. Hydrogen needs 1 and has 1. So that means we have 2 hydrogens, a total of 2. 1 bond counts as 2. Oh, perfect. They already got 2. So we have this times 3 because we have 3 hydrogens up there. Okay, now let's talk about NH3. This is going to be probably the most complicated one. So now we have to think, how are we going to set this up? For the most part, it's going to be centered around the bigger atom. But how it's actually said is it's mostly going to be around the most electronegative atom, which means the one that attracts the least amount of electrons and therefore attracts the most amount of protons and therefore attracts the most amount of atoms around it. So that means this N is going to be the centerpiece and the hydrogens are all going to surround it. So we're going to have an N, we're going to have an H, bond H, bond H. Okay, now let's think about how many electrons there are. N is 5, like we said earlier. H is 1, like we said earlier, for the same reasons. So that means we have 5 plus 6, 7, 8. So now we have a total of 8 to deal with. So far we've used 6. This hydrogen's full because it only needs 2. That counts as 2. Hydrogen full, hydrogen full. We have 2 more to play with. This nitrogen only has 6 and it needs 8, but we have 2 more to play with. Now again, lone pairs, that's me. Lone pairs want to be as far away from the other things as possible, and sometimes these themselves will even swing around to adjust so that they are as far away from the lone pairs as possible, because remember that this hydrogen still has electrons it still has 1 or 2 electrons surrounding it from that bond. So these are actually going to swing further over here. So if I were to redraw this, it would look more like this. That would be the more accurate representation of what ammonia is. Okay, so now those are the pairs. So we haven't even starting talking about bond energy stuff yet because we needed to draw the things in order to do it. Oh yeah, hold on. 2. There's 2 of them. Okay, I think we're good with this graph. Oh, maybe. We'll see. I'll draw it later if I need it. So, We have two of those. Remember how before I said you actually have to add energy to break a bond, and you need to, and form a bond releases energy just because of the nature of that graph. Hey, I needed it. Forming that bond brings us down to a more negative energy than we began with. Breaking that bond means we have to go from a low negative to a higher negative or even zero, which means that's us pumping in energy. So what we do is we say, well, we have an N2. Oh, nice, N2. We have an N2. This triple bond of N's gets broken. This triple bond of N's gets broken. So that means that's how much energy we have to put in. So that would be positive. This 3H, we have H bond, oh, N, nice. Ew, that's gross. H, 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 H. Okay, these all get broken because we need to then basically we need to basically break them apart like Lego pieces, reassemble them in a new structure to form that. This gets broken, that gets broken, that gets broken. So that means we have to pump in some more energy to break them, so that way we can separate them. We have E plus times 3 because we're doing this 3 times. Okay, now we need to form these new ones. We're going to have N, H, H, H. These now are newly formed, so we're going to circle them like that. Because it actually wants to become this bond, it means that we can then take energy out. So that means that we're taking E, 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 minus, 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 to form it. And then we're multiplying this whole thing times 2 because there are two total ammonias. So now if we sum up how this works, remember that the amount of enthalpy in the system is going to be the amount of positive minus the amount of negative. So that means that since these are the positive ones, that's going to be change in H reactant minus change in H product. And that is going to give you how much we have. Now, just so you know, these are really faint on the screen. These are negatives here. So it's not like we're going and subtracting off a negative number. That minus sign accounts for the fact that these are already negatives. If you really wanted to make it like that, you could say, well, the change in the change in heat is equal to the sum of all interactions of energy. That was a horrible sigma sign. The sum of all energy interactions, and then account for these negatives when you plug them in with the bond energies that are given to you on the table. But for the most part, you're just going to see reactants minus products, because that fact that it's a minus E right there is not going to be taken into account when they give you it on your chart here and they're all positive numbers. Because this could just be flipped the opposite way, and then all of a sudden now these are all the negatives and these are all the positives. So that's why it's then reactants minus products, because then that negative is taken into account. That then becomes change in H reaction, and then when you go and calculate it out, which I'm going to do now by erasing everything and allowing myself to actually do it, we have change in H RxN is equal to change in H reactants minus change in H products. So our reactants, what we're going to see is we're going to have change in H reaction is equal to 1 triple nitrogen bond. So we're going to see an N plus, because now we have this one, plus 3 single H bonds, minus 2, because now we got to products, minus 2 times 3 N single bond H's. Okay, so that's all that means. That's us saying there's 3 times 1 of triple H's, 1 times 1 or not triple H's, single H bonds, 1 times 1 of a triple N, and then 3 total NH3s in one molecule, 2 molecules, so 2 times 3 NHs. So now when we plug all of that in, we should get 941 kilojoules per mole plus 3 times 432 kilojoules per mole minus 6 times 391 kilojoules per mole. So now when this is done right, this should, assuming I've done my math right, check out to be negative 92.2. And unless I've written something down wrong, something like that. Where the heck is my calculator at? In my backpack still. Nice. I'm very prepared for this. Can't you tell? We have 941 plus 3, 432 minus 6, 391. Hey, would you look at that? Negative 109. That's not super close to that. But that's okay, because if you have a different process going on, you're going to have a slightly different energy that's going to go somewhere. It's going to be released from somewhere. And again, all of the values given on this chart here are all averages of doing this thing 100 times. So they're not perfect values. You're not going to get a perfect number. You're just going to get something really close. Now, on an ideal problem, it will actually be the real number. And they probably won't give it to you unless it's pretty close. But in this instance, it does say that the change in H of the reaction, assuming I didn't type it in wrong. Did I type it in wrong? 342, 432, right? Minus 6, 391. I'm going to double check really quick. I want to just make sure, because that should be pretty close. That seems a little too far off for my liking. NH is 391. Yeah. HH is 432. Yeah. Triple bond N is 941. Yeah, I guess so. Okay. So that would be then equal to negative 109 kilojoules per mole. Let's go back to our datum, back to our original number that proves how much there is that was actually given to me on an FRQ, negative 92.2. Hey, that's pretty close. Pretty close. Good enough for my sake. So that's how you would then go and do it. And that is really the essence of what the difference is between bond energy and enthalpy of formation. It's just dependent on how it works. It all stems back to this graph. The real key thing here is this graph. If you have, this is would be distance, this would be PE, and your normal graph looks something like this at any one, then that means that that's a really bowed out graph. Should be better now. That's a little better. What that means is that in order because this is a really negative low number, it's a really negative low number, in order for you to separate this thing enough, I don't know. You know what? I have golf balls. Would you look at that? So let's say you have your, I don't know, your nitrogen there, and then you have two H's here. In order for you to separate this thing enough, so if you're traveling up on this here, you're increasing the distance, you're forcing these two apart. In order to get the distance wide enough for this atom to now want to join with this one, you have to pump energy in. And then once you want it to join with this one, then you're going to start talking about a different curve, because the energies are slightly different, even though they'll look pretty similar. So now let's say that that's our new curve. I don't know. It could be something completely random. That actually looks really accurate to what it actually is, because this is a slightly lesser than this one. And I started off with hydrogen and then ending with the nitrogen one. So now that this is separated just enough to where that this no longer wants to associate with that and now wants to associate with that, we're now going to then travel down on the green curve instead of up on the blue curve. We're going to travel down on the green curve, and it's going to go as these get closer and closer together until we reach that point that we really want it to be at, where it's just locked. Or it'll, again, yo-yo back and forth. And then that counts as a bond. And so every single time you pump the energy in to separate your original two, that's you pumping energy in, so therefore putting energy into the system, so that number is positive. And then when you then proceed to have these two that then come back together, because you're not doing anything for that, you're literally just letting the forces take over. You're letting the intrusive thoughts take in. No, you're letting the forces take over because work is force times distance when these things come together, and then yo-yo back and forth a little bit. Because you went from here to there was a change in distance that was due to some force, electric force. You now have a release of energy because now you've gone from a big distance to a small distance. And then we know that again, work is equal, that's a horrible pen, work is equal to negative P change in V, where if our change in V goes from big to small, work is positive. So that means positive work means positive for our sake, rather. So it'll be this. Once it comes together, we have a release of energy since work is an energy. And that is why those are switched around when it comes to that. Oh my god, that was painful. That was actually so long. Okay. Now let's talk about one more thing too. Let's talk about what happens when we have an equilibrium reaction here, because this is an equilibrium reaction. Let's pretend like it's not at 25 degrees Celsius, hence why I erased it up here. I definitely didn't do that on accident. If it's not at 20 degrees Celsius or 25 degrees Celsius, we're going to see a change in our equation. Instead of having change in G naught is equal to change in H naught minus T change in S naught, that still stays true because technically it always stays true because, again, if I explained it conceptually again, you'll just see that it's still the same thing, but now it's at different temperatures, so now the values are slightly different. Technically it always stays true, but these knots disappear because now it's not standard temperature anymore. So we now then have to go and try to calculate it. Now, some super smart chemist way back in the day decided I'm going to find a differential equation for it, and then tried to solve for the Gibbs free energy, and he succeeded. He basically found out that the change in G at any point in time is equal to the negative RT natural log of KQ. And then this became his, I don't remember the dude's name. I don't even think there was a name associated with this equation. Basically found out that when you do the equation for it, that the Gibbs free energy of the thing at any temperature is equal to the negative gas constant times temperature. So obviously it'll change based on temperature. And then the natural log of the equivalence point there. Now, if you wanted to compare that to how it actually would be at any point in time, you can just say change in G is equal to change in G. I want to make sure I say this one right because I don't have this one 100% nailed. I think that's it. Change in G naught minus RT ln lnq at any one point. I believe that's what it is. I want to make sure just before I say something that's wrong and then absolutely feel like an asshole. Oh, not minus, it's a plus. Because technically if you're at KEQ, the change in G from the original is going to be equal to 0. So then you can just subtract this over. Or this would be 0 because one of them would be 0, this would subtract over, we'll get that equation. Okay. So let's ignore that one because that one's not important. Let's now talk about how this thing works. Again, we're going to have our change in H, our Xn is equal to negative 92.22, not 9, 2 kilojoules per mole. Okay. Let's talk about it in terms of this now. So, if Gibbs free energy is negative, if the reaction is spontaneous at any one point in time, if this is negative, then that means that whatever happens, this term must also stay negative. It's already negative. Temperature can't be negative because we can't have a negative Kelvin. This is not a negative constant. And natural log exists as a negative. Let's not do that. Natural log exists as a negative where this is 1, this is the y, and this is the x-axis. And this would be natural log of x. Natural log exists at a negative only between 0 and 1. So that means this KEQ must be greater than 1 to maintain a positive value that's not 0 for this, so that way that stays negative and therefore spontaneous. Hey, though, if the KEQ is greater than 1, if KEQ is greater than 1, that means a tendency for this equilibrium reaction to go from reactant to product. Because a KEQ of greater than 1 means that there's a tendency for this thing to go that way and to stay with a lot of products. Oh, wow, everything's connecting. So that means that's there. Now let's say we wanted to have this Gibbs free energy be a positive number, which means we as the chemist have to put energy into the system to make the thing work. So that means this Gibbs free energy is positive. We need a way to make this a positive then. That is a positive number. It starts out negative, so we need to make something negative. That's a positive number. That won't change it. That's always a positive number. That won't change it. ln KAQ is equal to a negative number only between 0 and 1. So that means if KEQ is between 0 and 1, then what we'll get is we'll see a tendency for this thing to switch to reactants. So we'll see it go from that side to that side. It'll adjust, which is exactly what would happen if you had a G that was positive. It means that it would go from that side to that side if you have an equilibrium reaction. And you wouldn't have to pump anything in if you wanted to go from that to that. But you would if you wanted to go from that to that. Hey, that makes perfect sense. Good enough. Okay. Now what happens if G is equal to 0? Well, the only way to get this term to equal 0 would be to get temperature at absolute value, which you'll never do because it's impossible. People are really, really close, but never actually at absolute value because that would mean 0 motion, not even vibration, which people haven't figured out how to do yet. But natural log KEQ can equal 0 only when KEQ is equal to 1. Well, when KEQ is equal to 1, 0, nice. I wrote the right number there. I'm really on it right now. When KEQ is equal to 1, then that means that there's an equal tendency for this thing to go to reactants to products or products to reactants. So therefore, you don't have to put any energy in, and it doesn't have to suck any energy out to go from there to there. There's a perfect amount in the atmosphere and a perfect amount in the reaction to where it'll go from there to there without hurry, there to there without hurry. That's it. That's all it means. That's it. Simple as that. So that's the non-standard state there. Okay, what else is there that I can talk about while I'm here talking about things? I think that's the main cover that needs to be done. Obviously, based on that last equation I showed, you can derive what KEQ equals from it, and it's e to the some power that's stupid. Yeah, basically it. So, yeah, honestly, we're good. That's it. I got the first take for the bond energy one. Wow, that is quite the achievement. Okay, I will hopefully get this posted by tonight, if not tomorrow morning. Woo!